Using the LHC, scientists made the historic discovery of the Higgs boson, sometimes known as the God particle, whose existence had previously only been predicted by the Standard Model of Physics. François, Englert, and Peter Higgs, whom the discovery is named after, won the Nobel Prize in Physics for their 1964 prediction of the particle's existence. Now, researchers working together on the LHCb experiment are adding to the already magnificent legacy of the Large Hadron Collider. The discovery is hinted at the promise of a portal that's going to open, and the generally held belief that it would resemble a scene from the most recent season of Stranger Things. What is and isn't the Large Hadron Collider at CERN doing? Will CERN truly produce a black hole? Let's find out. How would your body react if you placed it inside a particle accelerator? The situation appears to be the beginning of a terrible Marvel comic, but it actually clarifies our preconceptions regarding radiation, the susceptibility of the human body, and the fundamental nature of matter. By accelerating subatomic particles in strong magnetic fields, and then tracing the interactions that result from collisions, particle accelerators enable physicists to study subatomic particles. By delving into the mysteries of the universe, colliders have entered the zeitgeist and tapped into the wonders and fears of our age. The European Organization for Nuclear Research's CERN Large Hadron Collider, LHC, was given the task of producing tiny black holes so that physicists could discover extra dimensions as early as 2008. When the LHC was still being developed, some scientists thought it would produce a black hole, leading the Italian physicist Francesco Calogero to write an essay in 2000 titled, "Might a Laboratory Experiment Destroy Planet Earth?" People have been overreacting about this very, very big particle accelerator since Bill Clinton was president. In 2009, John Oliver interviewed a science teacher who thought the LHC experiments had a 1 in 2 chance of creating an Earth-destroying black hole. Oliver also interviewed actual scientists at CERN, who was much more reassuring but also much less funny. That essay started years of commentary, both serious and not, about the LHC killing us all. It came as no surprise when 2 people filed a lawsuit to stop the LHC from operating, lest it produces a black hole strong enough to destroy the world. But physicists argued that the idea was absurd, and the lawsuit was rejected. To many, this sounds like the plot of a disastrous science fiction movie. 2 researchers proposed in 2011 that many black holes gravitationally bind matter without significant absorption, which is to say that many black holes drift around, unnoticed by anyone. And yes, for all anyone knows, the LHC might have created black holes no one has been able to observe, and yet Earth is still here. The LHC's core is a ring that circles the LEP tunnel. It has a diameter of only a few centimeters, is evacuated to a greater extent than deep space, and is cooled to within 2 degrees of absolute zero. Protons belong to a category of heavy subatomic particles known as hadrons, which accounts for the name of this particle accelerator. In this ring, 2 counter-rotating beams of heavy ions or protons are accelerated to speeds within 1/1,000,000% of the speed of light. At 4 points on the ring, the beams can intersect, and a small percentage of particles can crash into each other. At each point of collision are massive magnets weighing tens of thousands of tons and banks of detectors to collect the particles produced by the collisions. At maximum power, collisions between protons will occur at a combined energy of up to 13 TeV, about 7 times greater than has been achieved previously. For decades, physicists have used the so-called Standard Model for fundamental particles, which has worked well but has weaknesses. First, and most importantly, it does not explain why some particles have mass. One of the goals of the LHC project is to understand the fundamental structure of matter by recreating the extreme conditions that occurred in the first few moments of the universe according to the Big Bang model. The Higgs boson, which had never been observed and was supposed to be created only by collisions in an energy range that was unavailable for experiments before the LHC, was proposed by British physicist Peter Higgs in the 1960s as the particle that had given other particles their mass at the beginning of time. The long-sought Higgs boson, a particle required to explain how particles gain mass, was then discovered by the LHC in 2012. The Standard Model makes some arbitrary assumptions, which some physicists have suggested may be resolved by postulating a further class of supersymmetric particles. These might be produced by the extreme energies of the LHC. Secondly, the Standard Model requires some arbitrary assumptions, which some physicists have suggested may be resolved by looking at asymmetries between particles and their antiparticles. These might be produced by the extreme energies of the LHC. Thirdly, the examination of asymmetries between particles and their antiparticles may provide a clue to another mystery: the imbalance between matter and antimatter in the universe. With that significant achievement, the LHC made its way into popular culture. It was depicted on the Megadeth album cover for Super Collider and served as a narrative point in the US television series The Flash. Unlike a NASA probe sent to Mars, CERN's research doesn't produce stunning, tangible images. Instead, the study of particle physics is best described by chalkboard equations and squiggly lines called Feynman diagrams. However, despite its achievements and glamour, the world of particle physics is so abstract that few understand its implications, meaning, or use. The Bohr model of the atom was created by Aga Bohr, a Nobel laureate, whose colleague Ola Ulfbeck has even gone so far as to dispute that subatomic particles are anything more than mathematical constructs. Which brings us back to the question we started with. What happens when a stream of subatomic particles flying at almost the speed of light collides with human skin? Perhaps because particle physics and biology are so conceptually dissimilar from one another, some expert physicists struggle to come up with an answer to this topic as well. In a 2010 YouTube interview with members of the University of Nottingham's Physics and Astronomy faculty, a number of academic experts confessed that they were unsure of what would happen if a hand was placed inside the proton beam at the LHC. Professor Lawrence Eves was equally cautious about drawing conclusions. "That's a good question. I don't know the answer. Probably be very bad for you. By the scales of energy we notice, it wouldn't be that noticeable," he said, likely with a bit of British understatement. Would I put my hand in the beam? I'm not sure about that. However, Anatoly Bugorsky, a Soviet physicist, stuck his head inside a particle accelerator on July 13, 1978. On that fateful day, Bugorsky was inspecting broken machinery at the U-70 synchrotron, the largest particle accelerator in the Soviet Union, when a safety mechanism failed, sending a beam of protons hurtling toward him in a Phineas Gage-style direct hit. Although proton therapy, a cancer treatment that uses proton beams to destroy tumors, was developed before Bugorsky's accident, the energy of these beams is generally not above 250 million electron volts, a unit of energy used for small particles. So it's possible that at that time in history no other human had ever experienced a focused beam of radiation at such a high energy. Protons from the solar wind and cosmic rays are prevented by the Earth's atmosphere, and proton radiation is so uncommon in radioactive decay that it was not discovered until 1970. Proton radiation is a rare beast indeed. Unless a radioactive source is consumed, more common dangers like UV photons and alpha particles cannot get beyond the skin. However, when Apollo astronauts protected by spacesuits were exposed to cosmic rays containing protons and even more exotic forms of radiation, they reported flashes of visual light, a harbinger of what would welcome Bugorsky on the fateful day of his accident. For example, Russian dissident Alexander Litvinenko was killed by alpha particles that do not so much as penetrate paper when he unknowingly ingested radioactive polonium-210 delivered by an assassin. Anyway, the young scientist was transported to a clinic in Moscow with half his face swollen, and doctors expected the worst, according to an article published in Wired magazine in 1997. Bugorsky immediately saw a tremendous flash of light, but felt no pain. By attacking a cell's genetic programming, ionizing radiation particles like protons can kill a cell, prevent it from dividing, or induce a cancerous mutation. Cells that divide quickly, like stem cells in bone marrow, suffer the most. Since bone marrow is where blood cells are made, Radiation poisoning frequently results in infections and anemia from red blood cell and white blood cell losses, respectively. However, in contrast to the widespread distribution of nuclear fallout that affected many victims of the Chernobyl accident, or the bombing of Hiroshima in Bugorsky's case, radiation was concentrated along a narrow beam through the head. But as the beam flew through Bugorsky's brain, it deposited an incredible amount of radiation energy, hundreds of times larger than a deadly dose by some estimations, which may have largely spared the more delicate tissues, such as bone marrow and the gastrointestinal tract. Therefore, Bugorsky is still alive today despite having at least 6 generalized tonic-clonic seizures and having half of his face immobilized, giving one side of his head a bizarrely youthful aspect. Bugorsky's epilepsy, likely caused by brain tissue scarring from the proton beam, has also left him with petit mal or absence seizures, which are much less dramatic staring spells during which consciousness is briefly interrupted. Grand mal seizures are commonly known as these, and they are the seizures that are most frequently depicted in film and television, involving convulsions and loss of consciousness. Although cancer is frequently a long-term side effect of radiation exposure, there are no reports that Bugorsky has ever received a cancer diagnosis. As terrifying and amazing as the inside of a particle accelerator might be, humanity has so far survived the nuclear age. Despite having nothing less than a particle accelerator beam pass through his brain, Bugorsky's intellect remained unharmed, and he successfully completed his doctorate after the accident. The LHC was created to learn, among other things, why matter has mass, rather than to actually generate a black hole. In short, using the LHC to smash particles together was the quickest way to observe something called the Higgs field, a theoretical energy field that permeates everything and gives matter mass. In Geneva in 2012, CERN's Director General, Rolf Dieter Heuer, announced with great fanfare that his team had discovered the Higgs boson particle. Higgs and his collaborator François Englert, 2 British physicists who first postulated the existence of such a field and the particles that make it, shared the Nobel Prize because the particle Heuer and his team discovered in 2012 matched theoretical calculations. Funny enough, the Nobel Foundation passed over the CERN team. Perhaps they were upset about the entire black hole thing. One theoretical physicist, Erez Etzion, thought it might help us understand other dimensions when the LHC was first turned on in 2008. However, there were hopes beyond just discovering the Higgs boson, which mostly just answered an obscure question about matter that few laypeople had ever bothered to wonder about. None of those predictions came true, and the LHC went years without making headlines, save for in 2016, when a weasel got into the wiring and died, bringing the entire system to a halt. In 2018, the LHC was shut down for maintenance. According to CERN, upon its restart, it would achieve higher beam intensities. At the time, the outage would extend for 2 years. Now that the LHC has restarted, it appears that the upgrade was successful. CERN is celebrating the discovery of 2 new tetraquarks and the previously described type of pentaquark. Niels Tuning, the physics coordinator for the Large Hadron Collider Beauty, LHCb, said this in a CERN press release. "The more analyses we perform, the more kinds of exotic hadrons we find. We're witnessing a period of discovery similar to the 1950s, when a particle zoo of hadrons started being discovered, and ultimately led to the quark model of conventional hadrons in the 1960s. We're creating Particle Zoo 2.0. It is thought that quarks, which are subatomic elementary particles, constitute the basic constituents of matter. Hadrons, which are typically composed of 2 to 3 quarks, are also known as tetraquarks and pentaquarks. These larger groups of up to 4 or 5 quarks are far less common. These new quarks are unique due to their charm, literally. These so-called exotic quarks are often made up of charm quarks and charm antiquarks. Up, down, or strange quarks and antiquarks make up the remaining quarks. However, the components of this newly discovered pentaquark are a charm quark, a charm antiquark, an up and down quark, and, pardon the technical term, a strange quark. According to CERN, this is the first instance in which a weird strange has been discovered in a pentaquark. Regarding the tetraquark, it stands out not just for being the first to be discovered in a pair, but also for having two electrical charges. Does that imply that it will only take a few more experiments for the LHC to create a gateway and zap a demogorgon into our world? We should probably keep our expectations in check, given that the LHC has previously led to the discovery of tetraquarks and pentaquarks in the past. Will a black hole be produced by CERN? Well, people who were concerned that CERN will produce a black hole should exhale in relief. According to CERN, there won't be any dangerous black holes produced by the LHC. But even if some tiny quantum black holes were to result from the collision, they would be absolutely safe. It asserts that the existence of small black holes created by the LHC is impossible, citing Einstein's general theory of relativity. The statement adds, there are, however, some speculative theories that predict the production of such particles at the LHC. All these theories predict that these particles would disintegrate immediately. Black holes, therefore, would have no time to start accreting matter and to cause macroscopic effects. Even if the LHC did produce a black hole, it would be so minute and minuscule in quantum terms that it would not escape the accelerator and endanger the world. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.